I'd like to cover just one other sorting algorithm in this chapter. That's known as the counting sort, or sometimes the bucket sort. This is a sorting algorithm that's incredibly fast, but it works only for integers. It's best for lists that have many duplicates in a small range of integers. So you can think if I have a list that has 100 numbers in it, but all of those numbers are between 1 and 10, so let's say maybe I'm sorting a list of ratings, then bucket sort, or counting sort, is very efficient for this. So the basic idea behind the counting sort is we're going to keep a count of how many of each one of the values is in our list, which we can do in a single traversal of our input. And then we will use those counts to fill up some output list, which we can do in another single pass. So let's see how this works. So given some input, in this case we have only the values 0 through 3. So in this case, the size of our input, we could say n is still 8, but the range of our input, we'll call that k, is only 4. So the way this works is we start with our input list, and we create a bucket for each one of the possible items. We do a traversal across that input list, and each time we see one of those items, we add one to the corresponding bucket. So we traverse our input list, counting each item as we go. So the first item is a 2, so we put a dot in the 2 bucket. The next item is a 0, so we put a dot in that bucket. Next item is a 1, so we count one of those. Then a 3, so we count one of those. We see another 1, so now we have 2 in that bucket, etc., 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 until we've passed through the entire list. So after we've finished this first pass, we've counted up all of the integers of each type, and now we have this list of the buckets. So we have a list that tells us the counts of each item. So we have a list that goes 1, 3, 2, 2, telling us we have 1, 0, 3 1s, 2 2s, and 2 3s. Now what we can do is traverse this counting list, and for each one of the items in each bucket, we'll add that many corresponding integers to our output list. So we have 1, 0, so we'll add 1, 0 to our output. We have 3 1s, so we'll add 3 1s into our output. We have 2 2s, so we'll add 2 2s to our output. 2 3s, so we'll add 2 3s to our output. And now our list is in sorted order. Just like that. All right, so let's see this in practice. So I have a function here, counting sort, our old generate random list, which just generates a random list of integers, but now it takes in a value n for the number of integers and the value k for the range of those integers. So notice it's generating random numbers in the range 0 through k. So here, if k is 4, it's generating the random numbers in the range 0, 1, 2, or 3, as in our pictographic example. And I'm generating 20 of those here. That'll give us an unsorted list. We'll pass that into the counting sort, and we'll get back our sorted list. So the design of our counting sort, we'll start by creating a list of counters for each value. So we want to have a list that has space, or these buckets, so we can add our counting into it. And we're going to scan our input list, counting 1 into each bucket. So we'll scan our input list, counting each value, and then we'll scan our counting list and fill our output by effectively dumping each one of those buckets. So we'll say scan our counting list and dump each bucket into the output list. And then when we're done, return output. So relatively straightforward. Let's see if we can implement this. So noting that our counting sort takes in a list of unsorted values as well as the integer k here. If we didn't have that integer k passed in, we could do some work to just scan through our input list once to figure out what the range of our inputs are. So step 1 is to create a list of counters for each value. So if we have k different values, we're going to need a list that has k spaces in it, each one of those a separate individual counter. So if we see a 0, we're going to add 1 to the 0 counter. If we see a 2, we're going to add a 1 to the 2 counter. Right? We want to have separate counters, and they're all going to be stored together in the same list. So we'll make a new list. We'll call it C for count equals an empty list. But we don't want to leave it as an empty list. We want to fill it with a bunch of zeros. So I'll say for I in range k, c.append 0. We've seen other ways we can make this work, but this is a nice liminal way to create a list of k zeros. We also need, it's not mentioned in our design, but we're also going to need an output list. So I'll just say up here, output equals the empty list. And this is the list we're going to fill in over time. So once our counter list is ready, what we need to do then is traverse our input list, adding 1 to the location in our counter list that corresponds to the value in our input list. So it's a bit of a strange operation, but it's very succinct. All we have to say is the counter at the current element plus equals 1. And this is really where the magic of the counting sort takes place. Here we're using the value from our input as the index for these counter buckets. So it says go to that location in the counter bucket and add 1 to it. So if the value is a 0, we'll add 1 to the first spot. If the value is a 2, we'll add 1 to the third spot. Here we'll traverse the entire list, counting up each item. And I'm just going to put a note here, note, using the item itself as an index. Once we've gotten through that loop, we have our counter list that has a spot for each of the possible items and a count of how many of those items were found in our input list. So the next step is to scan through our counting list and dump each one of those buckets by creating multiple integers in our output list. So we'll go for each item in our counting list. So for I in range, for the length of our C. Here we need the index because remember the index represents the actual value from our original inputs. So even though there's a 3 at the first spot in this counting list, that means we have 3 zeros. So we'll need to know that we're at index 0 when we see a 3 so that we can add 3 zeros. So to do that, we're going to have another loop here. We'll say for j in range from 0 to the size of this bucket. So we'll say to C of I. We're going to add that many items. So we'll say output.append I. So this one says for each counter, so for each one of those counter buckets, I'll say that counter bucket. The inner loop says add that many copies. So we're adding 1 each time through the loop. And notice the thing that we're adding is the index of which counter bucket we're on. If we're on bucket 0, we're adding zeros. If we're on bucket 1, we're adding 1s. Once we've done that, our output has now been filled with all the values, so we can just say return output, which that comment was literally the code, so I'll just uncomment it and off we go. So let's save our code and see if this works. Python counting sort. So as our input, perhaps not so random, we got a bunch of 1s, then 3s, then 2s, but it came out as 0, 1, 2s, and 3s. We can run it at a separate time just to make sure with sufficiently random values, we still end up with sorted output. Running again, also sorted. Awesome. So our implementation seems to work. But now how efficient is counting sort? So in order to sort our list, we have to do 2 passes of our data. So we have to do 1 pass to count up all the items. So for each item in our input list, we're going to add 1 to one of those buckets. And since we're doing that, just jump back to the code here real quick. To do that, we're doing that in a single step, right? We're saying go to that bucket at this index and add 1. We don't have to find the place in the bucket list to add it. We have this random access option because we're using lists that can be dereferenced by an index. So we're saying go to that specific location and add 1. There's no finding the location to add 1. It's just jump to that location, add 1, which means in order to count a single item in our input, it's a unit operation. It takes 1 step. And we have to do that for every item in our input, which means this takes order n time. If we have n items, we're going to count each one. So we're going to count n items. The next step is a nested loop though. So it's a bit difficult to see how long this will go because we have for I in range the length of C. If we have k total different values, so 0 through 4 for example, then this outer loop is going to go that many times, right? This outer loop says for each one of the buckets in our counting list, do the following. So the number of times this is going to repeat, if we say we have k different items in our input, then that's going to go k steps or k repetitions. But how much work is each repetition doing? Well, it depends. It's going to go from 0 up to the count of that bucket. But now if we sum all of these together, if I said take all of the values in bucket 1, add them to all the values in bucket 2, add them to the values in bucket 3, and to the values in bucket 4, if we sum all of these together, what would that equal? So for all of the runs of that inner loop, for each separate outer loop execution, how many total times is this loop going to run? How many total times are we going to need to append an item? Well, it's easy to see that our output list is the same size as our input list. And for each item in our output list, we're doing a single append, which means in total for both of these loops, the total amount of work they'll do is 1 append for each item in our list, which means overall, we're doing order n work in this loop as well. So if we can count all of the items in a single pass, that takes order n steps to just count 1 for each item. And then filling the output list can also be done in a separate pass, which again takes order n steps. Then in total, we're doing n plus n work. Notice it's not n times n, because we do one, we finish that one, and then we start the next. We're not repeating one of those for each time through the other. As we were doing, for example, with bubble sort, we would have to swap all the way to the end for one pass, and then we would repeat that again for the next pass, and we repeat that again for the next pass. With counting sort, that's not true. We're doing one pass to count, and then after that's done, we're doing a separate pass to output. So it's n plus n total work. So we'd say that's 2n, but again, big O ignores these small factors, so overall, this is order n steps. Now, we can say, generally speaking, if we have n items and a range of k values, that we have to do n plus k steps, because at one point we also have to pass through that counter list, which takes k total steps if we have k total values. But if k is very large, so for example, if we were sorting a list of all possible integers, so our counting bucket list had, I want to say an infinite number of buckets, but that's not possible. So we'll say a very large number of buckets. So let's say we were sorting values in the range from 0 to 10 million. Then we need to have 10 million spaces to store these boxes, even though we may only have 100 actual values. If we're using the value of our input as the index of our bucket, then that index has to be in that spot, right? If the bucket for the number 900 was at index 3, then we couldn't use this same system. So we need to have all those empty spaces even if we don't have numbers to fill them. So if we have a very large k, so again, if we're using an input that has possible values from 0 up to 10 million, then we need to have 10 million buckets. So that k value can actually become a very large value. So we say when we're doing counting sort, if we're doing so on a very narrow range of integers, then this is order n. Otherwise, we would have to say it's order n plus k, because that k term could be quite large, and it could dominate the overall complexity. Okay, and that is the end of this chapter. So we talked about complexity, and we saw searching and sorting as example problems in computer science where the complexity of our algorithm becomes important, because there's many different ways to search or sort through a list of information, but some of those are better than others. We also learned a bit about big O notation, which is a worst case measure of our algorithms. We learned about a bunch of different classes of big O, so we saw constant time, where our algorithm is always doing the same amount of work. We saw linear time, where if our problem size gets bigger, the amount of work we have to do scales linearly with that, so order n. We also saw quadratic time, so n squared time, where for each item in our list, we have to, for example, compare it to all other items. So we end up with having squared amounts of work relative to its input size. So if our input size goes up by 10, we end up having to do 100 times more work. And we saw logarithmic time, which is less than linear time, but a little bit more than constant time, where the amount of work goes up as our problem size scales, but it does so by a non-linear or a less than linear amount. So for example, we saw the binary search algorithm. If our problem size doubles, that's just one more comparison with the binary search algorithm. All right, we'll return to the problems of searching and sorting, primarily sorting, at the end of the next chapter when we learn about recursion, which is a powerful technique for supporting this concept of divide and conquer in order to simplify the amount of work we have to do by decomposing it into smaller subproblems. That's it for this video, and I will see you in the next one.